Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aryabhat College, University of Delhi. So in this series of advanced data structures and algorithms, the topic which we are presently going through is about B trees, and in the context of B trees, what all we have covered till now in our previous lectures was initially we looked into what actually B tree is and why it is required. So basically it's a type of data structure which is required for the storage which is to be done, or which is to be implemented for secondary storage devices. So it's a data structure to be to store the data on secondary storage devices. Then after that we looked into what is actually searching or how are we going to search in case of B trees, and apart from exploring other properties of B trees, that is comparison with binary trees and so on and so forth, we also looked into insertion. So when we talked about insertion in our previous lectures, there was a situation that insertion is kind of inserting a new key, and that is supposed to be done only on the leaf node. So now after searching and insertion, another common operation which is kind of prevalent in any of the data structure is deletion. So when we talk about deletion in B trees, that means we are talking about deletion of a key. Now when we compare this operation of deletion in case of B trees with the operation of insertion, we find that the insertion is a relatively simpler idea as compared to deletion, or we can say that other way around, deletion is more complicated than insertion. Now the question says why? Because when we talk about inserting an element is always insert at the leaf node, but when we talk about deletion of a key from can be from a leaf node, or we can also delete a key from the internal node. So from that point of perspective, we need to rearrange the nodes of children accordingly. So if it is an internal node, properties of internal nodes, that means the number of minimum and number of maximum keys and children has to be attained properly. Or if it is for the leaf node, that means if we are deleting a key from the leaf node, not from the internal node, so again we have to rearrange the keys and keys. I mean, we need to look for minimum and maximum number of keys. But if we are going with an internal deletion from an internal node, then number of children also kind of are to be rearranged. So the bottom line is deletion requires a more careful execution as compared to insertion. Or even if I kind of arrange the complexity in the sense ease of implementation, not the time complexity which I am talking about. So if I am talking about ease of insertion, so search is the easiest operation, then comes the insertion. Insertion also we need to look for the splitting of nodes. Then there was a situation when the height of the tree was increased. So all those situations need to be carefully monitored and arranged accordingly. In case of deletion, so after searching the complicated the complicated operation is insertion, and as compared to insertion, the more complicated information operation which we have is about deletion. So when we talk about deletion, if we see that operation of deletion carefully, or if we give a conscious thought about this deletion, it says that basically deleting an element from a B tree node, it is consisting of basically three main steps, or we can say three main events. What are the events? So one is, first you need to search the node from where that key is to be deleted, whether it exists or it does not exist. So one is searching the node where the key to be deleted is there. Then we are actually deleting the key, that means we are removing that key from that particular node, and after that balancing of tree is also required. Now, why this balancing of tree is required? Recall the situation of insertion in which when we inserted the node, when we inserted a key in a node, it the node gets overflowed. Similarly here, if we delete a key, there are situations in which there are situations in which your node may get in, or your node may enter in an underflow situation. Now, if it is an underflow situation, then again the balancing of keys or balancing of tree, more specifically if we can say, are required. So, first of all, the key is to be searched. So, search operation is anyways kind of we can say tied up with the insertion as well as with the deletion, because we need to search for the key with either we need to search for the key which is to be deleted, or we need to search for the place of the key which is to be inserted. So, search is kind of we can say it is inbuilt. Then the key is to be deleted, that is the second we can say event, that is the second step, and then we need the balancing of tree if it is required. Now, why this balancing of tree is required? Because deletion can trigger a situation of underflow, as I told you. So, underflow basically occurs when a node contains less than the minimum number of keys it should hold. That means already the node was on the minimum threshold, and when you are going to remove one more key from that node, it is actually getting into a situation of underflow. So, that is one idea in which you need to look carefully for the deletion thing. Now, after deletion, just like the insertion, we need to make sure that the deletion does not violate the properties of B trees. What all properties of B trees I am talking about? So, in insertion, we ensured that the node did not get too big due to insertion, and vice versa in deletion or during deletion, we need to ensure that the node does not get too small. Now, we also need to remember the root which is allowed to have fewer than the minimum number of t minus 1 keys, so where t is actually the we can say minimum number of keys. So, one, it is the root which is not following or which is allowed to we can say disobey the minimum number, the constraint of the minimum number of keys. Other than that, if it is an deletion is happening from, let us say we can say in internal node or in leaf node, all others need to follow the minimum number of keys existing situation. Now, in insertion algorithm, we need to please recall that we need to back up if a node on the path to where the key was to be inserted was full. So, likewise, if we talk about the deletion, so we might have to back up if a node along the path to where the key is to be deleted has the minimum number of keys. So, even the node is already in the minimum number of situation, then you are removing one more key, then in that situation you might have to back up if the node along the path where the key is to be deleted has the minimum number of keys. Now, deletion process, if we talk about, so deletion process actually deletes the key k from the subtree, let us say rooted at a particular a node, at a particular node x, we call it x. Now, this process guarantees that whenever this deletion process is being called recursively on the node x, the number of keys in x is at least the minimum degree t. That means minimum degree key constraints has to be followed by the number of keys during every recursive call of the deletion thing. So, deletion procedure, when it is a procedure to delete a key, k, assuming I am naming the key as k, and we are going to delete the key from this key, we are going to delete this key k from a subtree rooted at x. So, this process guarantees that whenever it calls itself recursively on a node x, the number of keys in x is at least minimum degree t. So, that constraint we actually need to follow hard and fast, that is must to be followed. Now, this condition, actually what is the requirement of this condition? This condition requires one more key than the minimum required by the usual B tree conditions. So, sometimes a key may have to be moved into a child node before the recursion descends to that child. So, recursively this delete procedure is being called, and this recursive procedure is actually descending to the child. So, sometimes a key may have to be moved into a child node. We will be definitely looking into all these kind of examples which I am talking about. Going with this condition, when the recursion descends to the child, we also need to say this condition, this strengthened condition allows us to delete a key from the tree one downward pass without having to kind of actually back up. Now, let us see this again. So, sometimes a key may have to be moved into a child node before the recursion descends to that child, and this strengthened condition allows us to delete a key from the tree one downward pass without actually having to back up. Apart from understanding this condition, there are two very common terms which are need to be understood before studying the deletion operation in a detailed manner. What are these two terms? One is in order predecessor, another one is in order successor. Now, if you are familiar with B trees, which I am sure you people are, so this in order predecessor and in order successor are common terms. So, when we talk about in order predecessor, this is actually the largest key on the left child of the node is called in order predecessor. So, consider the if we are looking for in order predecessor of a key x, that means the key which is occurring just before the key x, if we are going to take an in order walk. So, the largest key on the left child of that particular x is the in order predecessor of x. On the similar lines, if I am talking about in order successor, so in order successor is the smallest key on the right child of a node is called in order successor. Now, here kind of just we can say these definitions are twisted in context of B trees, because a B tree node is having more than one key. When we look these definitions into in the context of let us say binary trees, these definitions are kind of we say little more easier, but here in a node we are having n number of keys. So, the largest key on the left child of the node is called in order predecessor, and the smallest key on the right child of the node is called its in order successor. So, here the in order successor of the node or in order predecessor of the node is to be important, is actually important. Now, before going into the the implementation of deletion operation, let us give a quick recap, or let us give a quick recall to the definition of B tree again, because that definition of B tree is going to give us the maximum and minimum number of children and a formula for that. So, I am kind of just recapping that thing. So, a B tree of degree m, where the degree of B tree is considered as m, a node can have maximum number of m children. So, I am assuming here that my m is 3. So, a B tree of degree 3 can have the node can have maximum 3 children or m children. Then a node can contain a maximum of m minus 1 keys, that is we can say 2 keys. here in case of when m is 3. Apart from that, a node should have a minimum number of a ceiling of m by 2 children, that is 2 children here in case when m is your 3. So, 3 by 2 is 1.5, but if I am going to take the ceiling of 1.5, it is going to be 2, and a node should contain a minimum of m by 2 mod of m by 2 minus 1 key, that is actually your 1 in case of 3. But please remember that minimum number of keys, or this minimum number of keys actually does not go with the root node is an exception. So, this was actually a kind of quick recap or quick recall of the deletion, the properties of B tree in terms of its degree, and correlated with the maximum and minimum number of children, maximum and minimum number of keys in a node. So, why we just give it a recall, because we will be requiring these properties in order to check the underflow when we perform the deletion operation. So, as in insertion, there were so many cases when we did insertion, that there was a case in which the insertion is simple, then there was a case in which the insertion was resulting in an kind of overflow, then it was triggering the split of the children, and there was also a situation in which this overflow is being resulted in an increase in the height of the tree. Similarly, if we talk about deletion, we have 3 main cases, or 3 main cases for deletion operation in a B tree. So, we will take them one by one. So, my first case is the key which we are going to delete, it lies in the leaf. Now, here we also need to see that the key which we are deleting is lying in the leaf, or it is lying in the internal node. Then also the equations or the calculations are to be taken care of. So, if the key deleted lies in the leaf, and there are again 2 separate cases for this particular case. The deletion of the key does not violate the property of minimum number of keys a node should hold. So, that we can say is the simplest idea, that we are going to delete a key, it is available in the leaf, and even after deletion of that particular key, minimum number of keys a node should hold, that constraint or that property is not violated. So, we can just simply delete a particular key and we are happy with that. Now, another situation is the key which we are going to delete lies on the leaf, but on the contrary, or as contrary to the first sub case, the deletion of the key violates the property of the minimum number of keys a node should hold. That means the deletion of keys resulting in an underflow. So, the key is to be presented, the key to be deleted is present in the leaf. Now, it can trigger an underflow situation, or it cannot trigger an underflow situation. So, both are the cases in which we need to see the situation. So, here let us consider one diagram of a B tree. This is a B tree where the value of m is 3. That means the minimum number of keys one node can hold is 1. So, now here let us assume the first sub case of the case 1. So, the case 1 is to delete the delete the key which is available on the leaf. So, let us say we are taking 32 for that matter, it is available on it is available as a key on the leaf node, and even after the deletion of it, 31 which is there, which is the we can say sibling or just next, the key which is available just next to 32 is 31. So 31 remains in the node and there is no underflow, because underflow here in case of m is equals to 3 will be triggered when you are going to delete the we can say keys, and there will be no more keys left in this. So minimum number here is 1. So this you can verify with the help of the figure which is given on the screen. In the figure we also have, if you can see, the root node 20 and 40. To the left of the root node we have 10, and to the left of 10 we have 5, and to the right of 10 we have 15. So one key is perfectly allowed when m is equals to 3. Now if you want to delete 32, there is no problem. This I can say is the simplest of all the cases. We can just delete the element 32. It is not triggering any underflow condition, and everything will be kind of will remain balanced even after kind of deletion of this element 32. So 32 was present on just on the right of 31 and we have deleted it, and the tree is actually in a we can say in a balanced situation and we are fine with that. So that was the simplest case. Now the next thing which comes up, or the next case which comes up, is the subcase of the case 1. So the case 1 says deletion of the key which is present at the leaf. It is going to kind of we can say trigger an underflow condition. Now for example, if this is going to happen in this situation, this is the same tree which we have just seen. Now we have deleted 32, 31 is remaining. Now what if we are going to delete this 31? So deletion of this 31 is going to result in an underflow. That means the minimum number of keys, or the constraint of the minimum number of keys, is going to be violated. Then what are we going to do? So here we have a solution that deletion of any key violates the property of the minimum number of keys a node should hold. In this case, we must borrow a key from its immediate neighboring sibling node in the order from left to right. In the order from left to right, if we talk about, that means we will be first looking into the immediate left sibling. If the immediate left sibling node is having more than minimum number of keys, then we can borrow a key from this node. But the condition here is the left sibling node must have the keys, or must have more than a minimum number of keys. If that particular node is also standing on the minimum number of keys, then obviously there is no point in borrowing, or you even can't borrow from left sibling. Or the second idea is we can check to borrow from the immediate right sibling node. So either we can borrow from left or we can borrow from right, but the sequence should be from left to right. So we will be checking the left sibling first. If it is in a situation to land a key to the right one, that is fine. Otherwise we will check with the right situation, right sibling. So here if we look into this figure, so on removing 31, the node containing 31 will result in an underflow. What is to be done? A borrow from the left sibling. Now left sibling is having two keys, 25 and 28. Is it in a situation to give you a key? Definitely yes. So even if we borrow a key from the left sibling, then that left sibling will not result in an underflow. So left sibling will be left with only one key, and that is perfectly okay if m is equals to 3. Now, but the point is, can we actually direct borrow? That means, can we really replace this 31 from 28? Can we do that? No. If we are going to do that thing in here, so what will happen? Please look into the tree and see that on the kind of left side of 30 there will be 25, and if 28 is going to be given to the node where 31 is present, 28 will take a position to the right of 30. So, that is again not acceptable, or that should not happen. So, how are we going to borrow? The borrow has to be done in a kind of a specific manner. So, this is the situation in which we are borrowing. So, 21 actually goes to the parent node where 30 and 33 are present, and 30 from that parent node. So, now that parent node is having 3 keys, assuming 28, 30 and 33. So, the median key is going to come down. So, 28 will go up to the parent node, 30 will come down, and the final tree will be like this. So, we have 28 and 33. So, left of 28 we have 25, then right of 28 we have 30, which we just kind of taken as a descendant from the parent, and 33 and 35 in any case are, we can kind of sit. So, here we have looked into kind of one particular case in which we have borrowed the key from the immediate left sibling, and it was in a situation to lend the key. Now, there can be a situation in which neither the immediate left sibling nor the right sibling is in a situation to give away the key. So, what are we going to, or how are we going to handle those cases? That still is is to be taken care of, and that we will be looking into our next lecture. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.